So thank you for the introduction. Okay. So first, let me explain what we're doing in nanorobotics lab. We're developing an instrument, actually, and we have many projects. I don't have the time to talk about everything here. But those are tools. We're developing toolbox, and one of the main applications is to reduce the dose of drugs to, in some case, like I said, in some case, replace chemotherapy by reducing the drugs and try to boost a bit what the research has done with the functionalization and drugs, things like that, and try to bring directly to the tumoral region. And so to help the doctor fighting the cancer and the different type of cancer. Here I'm talking about traveling the arteries to the microvasculature with different type of nanobots. And what I want to show here, we talked about a bit NASA just before the coffee break, and the bit is very similar. In robotics, you need to track a device, and you need to have a trajectory, go to point A to point B at the fastest route. And for that, you need feedback control. And if you use only one type of device or nanobot in this case, it's like trying to send a robot on planet Mars using one type of vehicle. And you know that we need something different thrust to go against gravity. If we go from planet Earth to Mars, and then we need to land on Mars, so it's completely different. And on Mars to explore the surface is going to be a different system. And the way we see it right now, in 2010, from all the experience that we did and all the calculation and the device that we developed, that's the same conclusion that we came. It doesn't say that. I know the next speaker will talk about probably artificial robot going to the bloodstream and things like that. But I'm talking what can we do right now in 2010 or the next few years to come. I'm in engineering. I was electrical engineering. I work in MIT 10 years mechanical engineering. Now I'm in computer engineering, so I'll be all my life pretty much engineering. I touch about every type of engineering except mining engineering, maybe. And when we try to attack this problem as a targeting, we look at artificial way, try to use the material and components and try to solve the problem. But we quickly found that there's limitation in physics. And we work with MEMS, things like that, and the technology today doesn't allow it to go at a scale, a small scale. We need to go down to, if you want to go to close to the tumor, go to the microvasculature, and if you look at the hydrodynamics of the vascular system, and you apply the physics, you need to go about 2 microns in size. That's what you need to do. And this is impossible with technology because a different thing. You got friction, stiction, you got a power issue, you got everything. And then I was thinking we need to get another strategy there. Then I said, what about if those robots actually exist in nature? What if exist in nature? So the first step would be try to find this robot. And then try to see, because we don't have, it's like we got this new toy, and try to find out about how it works. But we don't have the instruction sheet, so we start playing with it. Try to understand how it works. And then we integrate it into a computer program to have it to do what a typical artificial robot would do, and they call that a natural nanobot, if you want. Okay? So that was my short introduction here. So first, as you see, the medical robotics at different scale. So there's those big robots that try to do minimally invasive, thing like that, big platform. And then the camera peel, to the GI tracks. And then they put an integration mark. How the next robot will look like. Here's one of the things that we're working right now. Those are microparticles that contain nanoparticles. And we use dipole-dipole interaction. So somebody asked this before the coffee break, why an MRI? Because if you have a ferromagnetic material or superparamagnetic material, you saturate the material at about, for the best material, let's say iron cobalt, for instance, or it can be iron oxide, about 0.8 Tesla. The clinical MRI, typical MRI, I got 1.5 Tesla, which fully saturate the material. And if you use the gradient, orthogonal gradient used for slice selection, then you get the maximum force on the material for propulsion or steering around, stuff like that. And this is why that if you use an X-ray system, you need to create this high homogeneous field plus the gradient field, so you end up building an MRI system. That's why it makes more sense that use already an MRI system for that. The other thing is that the spatial resolution of the MRI is not as good in some instances as the X-ray system or CT scan. But if you put a particle into this, you can adjust that so it will create an artifact. It can be a different size, up to maybe 70 times the size. So it's like having a transmitter that emit a large signal and that allow you to be able to localize a smaller device that something will not be possible to see with CT scan. Okay, so here we use dipole interaction. Those nanoparticles, they're used for many purposes. If you use correctly, you can functionalize it for what we talk about, like we do with the research in nanoparticle, used on biodegradable polymers. If you put the right quantity of that and you mix with drugs, they can be used as nano engine because you can induce the force and propel there. They use also as a contrast agent. So they emit a signal that you can locate with MRI, and the controller now know what to do to correct the trajectory and put it back on track. And also, those nanoparticles create dipole-dipole interaction that help maintaining those aggregate together, increase the force, increase the signal, increase the amount of drugs that can be delivered if you want. And at the same time, you can control, if you synthesize correctly, the dipole-dipole interaction so they don't get stuck somewhere, but they take different form when we go to larger blood vessel to smaller one. Okay? So targeting, reaching target location inside the human body. Here's a real fact, is that, again, we go back to the space exploration. So we can send right now a robot on planet Mars very precisely where we want it. But if you want to go to the blood vessel at maybe 1 centimeters in the human body, it's not possible. And we spend much more money, actually, on the medical field than it is stuff like that. Okay, so when we talk about the targeting, there's nice things going on with ligand, with peptide, all kind of biomolecules to target this, the drugs. There's a lot of research going on, but like I said, we call it direct targeting. It's just that we try to localize and constrain in a specific place to help all those research to become more efficient there. So when you go into those blood vessels, I put a bit picture of blood vessel there with a map of a road map over there. So it doesn't matter how smart your robot is. If you can put the intelligence there, everything looks the same. I know me, I will get lost for sure. Even Einstein is with me, will get lost. There's no map, there's nothing. So you need a GPS system, right, for that. And the GPS is the MRI system. So that's why you can. Okay, those robots that go to the bloodstream, that's fine, they go randomly everywhere. But if you go from point A to point B, try to avoid other organ there, so you need a GPS system for that. That's why the MRI is good, because it's a controller, a sensor, gather information, act on the device, and maintain on the trajectory there, stuff like that. This is what the pilot, if you want, what the doctors see. We have all kinds of windows. I don't have the time to go in details over there. But this is all kinds of parameters we can adjust, and the computer software is there too, because different carrier will have different force induced and different thing. If you change the percentage of drugs, it will change also things. So everything is categorized, and you get 6 is the tracking of the device there.